everyone. Today we are talking about the first solid design principle, and letter S stands for single responsibility. That states that your class should be responsible for one single particular feature, and if you feel like you want to go back to your code and put a lot of new features and modify everything, that's probably a bad practice and you should go back and think about it. Because hopefully you have tested your code, it took some time, it was working well, and now you want to alter it. That's not good. So how we are going to structure our video today, we will talk about a couple of includes, we will define a boson structure. In particular, we will work with Z-bosons. Don't worry if you don't know a lot about it. We will just use two properties of Z-bosons, two features that should be suffice for our programming purpose. Then we will define an event because we are working with trying to work with events that we produce at LHC during proton-proton collisions. Finally, we will go to the main function of our program. We'll write the main loop and store our events. That should be awesome. So let's dive in and go to practical stuff. Starting with includes first. I would need IOStream. Also, we will use vector, so I will include that. For some distributions, we will need a random header. Another header that we will use for std bind method is functional. And last but not least, since we would like to store our results, we would need fstring. Now, we included important headers. What are other steps? We will define what is a Z-boson. Then we will define an event structure. Also, we would need a useful type def. And we will go to the main function. Alright, let's start with the boson. So, which properties it will include? We would need what is called net charge. And let's discuss briefly what it can be. If Z-boson can decay to two charge leptons, for example, to electron and a positron, it can also decay to neutral leptons and quarks, but doesn't matter at this point. What matters is we can have E minus E plus combination, E plus E minus, E minus E minus, and E plus E plus in terms of the charge. The real Z-boson would be only here because, as you see, net charge is 0 and Z-boson is a neutral boson. While here, net charge is either -2 or +2, and it's not a real Z-boson, and it's useful for us because we will test for this and remove it. So we will deal with some real physics. Now let me include also invariant mass. And invariant mass is about 91.2 GeV. And finally, I would like to generate a constructor. Okay. Moving to the next stage. We need to define an event. And in this event, we will have an event number. So let's say we store events and numbers go from 1 up to n, where n will be the last event that we manage to observe during collisions and store. Also, we will have, let's have std string for error, and this is just a useful naming for if number is, say, less than 50 for an event, we will call this error A, and if it's higher, we'll call it error B. And now let me define a type def of a vector of pointers to a boson, and we will call it vector of pointers to our boson, and we will use it here. We will call them just bosons. Now, what this struct can have in terms of member functions? Well, we can, let's say, add some event, we can modify an event number, we can modify error, we can remove some event, we can do some printing, we can also save it to the disk. And this is where the problem comes, because you may say store it to the disk, you may want to email it, you may want to store it in different formats, and all of this means you would have to modify a method how you store it, and this is bad practice, because as we discussed, what you have in your class, we will test it and we will forget about it because it works fine, we will be relying on it. So a stage where we save it, we will delegate to a specific, let's say, structure called saver to disk, and this structure will be responsible for saving. It is not the responsibility of an event to store itself. Okay, so this is very important. And at this stage, what I will do, I will just generate a constructor with all the fields, and we should be good to go to the new stage. Now, what is our next stage? We'll have our main function. Let's generate a couple of distributions. Let's start with a normal distribution which takes double the parameter, template parameter. Let's call it normal distribution. Now, what are the parameters that it takes? Well, as we discussed, mass is 91.2 and let's say sigma squared is 10. Now, for our charge, let's use a uniform distribution, uniform integer distribution. Let's indicate it by putting in here. And let's say it's a uniform from -1 to 1. We will use 0 value. Actually, let's do from -2 to +2, because as we discussed, there are cases of -2 and +2, and we will need just 0 because the boson is neutral overall. Now, let's also define a random engine which we will feed into our distributions, and I think it's called default random engine. And now also I would like to define some helper functions which I will call charge generator and mass generator. So I would use auto keyword, charge generator. We would use std bind. And how it works? Well, I'm taking my uniform in distribution and I feed in my random engine that we just created over here. And also I would define a mass generator following exactly the same procedure. I will use normal distribution and random engine. Now, for a vector of pointers to bosons that we will store, let's define this variable. Let's say now it's September, so September bosons. And we are going to main loop. For auto variable I, let's say we have 100 iterations plus plus I. What we will do? So let's get mass generator. Let's get charge, and you will see in a second how we are going to use those. First, we are testing for a condition. If our charge is 0 and mass satisfies certain criteria. So what is the criteria? Well, normally when we do analysis at CMS, we work with the mass of the boson, pole mass, which is 91.2, plus minus some window, and let's say this window is 15 GeV, which means from 76 to 106, and if it falls in this region, we will accept. So basically that would mean the following: higher than 76 and less than 106. Now, in our if statement, let's also print what is the charge, let's print also what is the value of the mass, and finally, if it satisfies our conditions, and it should because we are inside of the if statement, we will take our September bosons and we would push back our boson that we just generated. And we will do it by following. We'll create a new boson using the charge that we've got and the mass that we just generated. Alright, so far so good. This is end of for loop. Let's see how it works. So we are building our project, and you see charge is 0, and mass is 91, 84, As you can see, since we are printing it inside of the if statement, charge is always 0 and mass is never higher than 106 and always higher than 76. So all is fine. Now finally going to the point of saving our event, how we want to save these results. Let's say this printout over here. Well, let's go and define a specific structure which is called saver to disk, for example. Let's define a static which belongs to the structure function, call it save to disk. And what should be the parameters that we take? Well, since we are going to store events, let's take events. And for example, each collection of events we would like to store with a different name. So let's also include a file name. Now, inside the body of our function, let's start with offstream variable. Like that. Let's say output file, which we will create with the file name that we just pass into our function. Let's have a for loop, and this for loop, it will loop over the bosons which are inside of our event collection, and we would do the following. We'll take our out file and we'll say that here mass is equal to b invariant mass, and the charge is, here we will do b net charge, and we should be fine like that. Now let's use this saver to disk over here once we got the collection of September bosons. So let's define an event. Let's say event. Let's look up a constructor, event number, era, and vector to pointers of bosons. Let's say event number, we have 100 events, era, so since it's past 100, let's call it B, and here we will use our September bosons. Now we move to the saving stuff. We will use save to disk function, to which we need to give our event collection, and we also need to call it somehow. So let's call it September bosons txt. And that should be it. Let's run once again. Everything worked beautifully here. Let's see what we have in files that we just created under the name September bosons. As you see, 95, 95, 58, exactly the same information, perfectly stored, and the principle is illustrated. If you want to save something to disk, it's not responsibility of the event class itself, it's the responsibility of specifically designed structure, which is saver to disk, and it does this work perfectly. If you shouldn't do it in an event structure, because there are many functions that you can come up the event should do, but if you think deeper, it shouldn't. Alright, so to summarize what we have done today. We started with a couple of includes, we defined a boson structure, then we defined an event structure which uses bosons. In our main function, we started with a couple of distributions. We used it with the stdbind method to define charge and mass generators. We generated charge and mass 100 times. We tested for particular condition. When the condition was satisfied, we assumed it's a good Z-boson, and we stored those Z-bosons as September bosons, and we used a specific saver-to-disk structure to do that. This is a good programming practice of how you delegate some function that you think belongs to your class, but it actually doesn't, how you implement it separately, and then how you use it. See you next time. Stay humble, stay hungry. All the best.